Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is start a new unit where we're going to be studying root functions a lot more. So we're actually going to start off and we're actually going to study like inverse functions for a little bit. So we've just spent a lot of time learning about all sorts of polynomial functions and power functions like that. Now we're going to kind of switch gears and look at the functions that are basically the inverses to them, but I use the word basically because they're not quite perfect inverses. Like a square root function is sort of the inverse to a x squared power polynomial function, but not quite. And I will explain all that eventually, but it's going to take a little bit. And really from this point on in the course, a lot of what we do is we study a function and we study its inverse. And that's a really important thing because if you don't have an inverse function, you wouldn't be able to unpack what the original one does, right? So you sort of see inverses in Algebra 1, but you only see them with lines. But in order to really study them, we really actually need to start with something called function composition, which you might have also seen in Algebra 1, but if you didn't, I'm just going to kind of be explaining it here in this video, like from the basics. So to start off, just kind of motivate this idea of inverses and all this stuff, I want to review a really important thing, which is how you go about failing the vertical line test and hence not be a function. So basically what it is you have more than one output for one input, right? Basically the vertical line, if it passes through two or more spots, then it fails the test, okay? So I'm going to draw down here two graphs, one which is a function, one which isn't. And here's the simple one that we've seen a lot. So take x squared, right? This thing definitely passes the vertical line test. Anywhere you draw it, like even out here, it looks like it might hit a few, but this part is really still growing over and over and over and over. It just gets really, really steep. So this thing is a function. I'm actually going to delete some of those. I'll just leave that one. So this one, definitely a function. Check. And I'm going to draw this graph specifically. So this graph is not a function, right? The issue is right here and here. And so, those two spots make this graph not a function. And what we're going to study in the beginning of this unit is we're going to say inverses, and one of the things that you're going to see is that actually this is what the inverse for x squared should be, but we're going to see that we actually modify the inverse to make it a function. This right here is not a function, right? And we'll talk about that. But really, to even talk about inverses, we need to talk about this thing called function composition. So we're going to do that. But first, let me just write not function, right? So we'll come back to this whole idea of this slide. It's a really important idea, but we're going to need a little bit of tools to get there. So first thing I want to talk about is this thing, function composition. So basically, it is using a function as the input for another function or domain for another function. And you have kind of a weird notation. You can write it two ways, I guess, and I'll talk about those here. But basically, typically you're going to see this thing that kind of looks like the word fog, but it's not the word fog here. This is actually like a degree symbol, but it's not up. It's not a superscript. It's just a degree symbol on the main line, and that is the composition symbol. But basically, I can explain it with this picture. So the idea is like you're using a function as the input for another function. So it's like if you take some input, send it through a function g, you're going to get out this thing it's saying. Then what we do is we just use that function as the input now for f. So this kind of machine would be written f with a little circle thing g, and we read it, here, I'll do this. So we would write it like that, and it's a function of x typically, and that one, the other way you can kind of write it is like this. So here you can really see g is a function of x, okay? G is a function of f. And we read this thing right down here, we read this literally as f composed with g. That's how you read it, okay? This is just another kind of way we've seen functions before. We've seen it as these kind of like bubble diagrams. And you could think of the other direction. You can think of g composed with f as just take something over here, you apply f to it, and you get f of a over here, right? And then you're going to do g of that result, and you get g of f of a. And that's g composed with f. So this one right here is literally, typically again, some function of x. And here it's just g of f of x like that. Whenever you see this notation, the rightmost thing is what's actually acting first on the variable. Then this acts last. So it's when you see something like this, basically you can just think g is the outer function. F is the first thing to happen. And sometimes this helps people. I think this is kind of funny. If f was like a pizza and g was like a pineapple, right? Then a pizza, f, made up of pineapple is pineapple pizza, right? But if you do it the other way, it would be like a pineapple made up of pizzas. So that's literally like a kind of different way to think of the exact same thing. So all it is using a function as an input for another function. And believe it or not, this has a ton to do with inverses, and we'll get there and we'll talk about it. Not in this video, but you'll see. The plan for today, I just want to use this and do a few examples with this stuff. So we got two functions, f and g here, and I just want to literally write down what f composed with g of x is right here, and then this one is g composed with f of x, okay? And so all you got to do is, if you want to do this first, you can do this first, kind of think of it a little bit better. So g is, now let's color code some things here. So we'll do g is red and f is purple. So we have f of 3x plus 2, right? And then all f does, right, is it takes the square root of the input minus 4. But the input is now 3x plus 2. So I basically stick in here, right, the square root of my g, which is 3x plus 2, minus 4, right? That's all f does. Square root of the input minus 4. My input's now just a function, right? And you could simplify that a little bit. You could just say it is square root 3x minus 2. So that would be the new function that is using g as an input for f. All right, if I flip it around, so we'll use the same colors here. Oops. So now I'm doing g of f of x. And so that's going to be g, and then f of x is square root x minus 4. And all g says is take 3 times the input, right, and add 2. So I'm going to do 3 times the input and add 2, and the input is now just the square root of x minus 4. And for this one, you really can't simplify it at all. You can literally just kind of write square root, or 3 times square root x minus 4 plus 2. And that's all you can really do for that one. So that is just literally how you go about doing it. You just literally put one function in as the input for the other function. And the only thing you got to remember is the order. And based on this notation, f is being applied to g. and g is applied on the x first. So it would be like that. And this one just flips it around. So there's actually nothing wrong with doing this for 3 functions. You can absolutely do that. And another thing you want to make sure you can do is unpack functions. So here I give you a function h, and you can think of h as being built out of 3 functions. So what I want you to think about here is how we would basically do something where it's like h of x equals f of g of t of x. And so what I want here is to find these 3 functions, f, g, t, that you could combine, like let's say in that order, and then get h, right? And then down here, I give you 3 functions, and you can absolutely do this. You can absolutely do f composed with g composed with h of x, which is going to be f of g of h of x. And, we could honestly continue. There's problems I've seen where you actually have ... and you have like a ton of functions just kind of nested like this. So this one, kind of build it up. This one, break it down. That's the idea. So if I was looking at this, one of the things I see kind of as like an outer function is that I see it's something cubed, or squared, minus 3. So I might say, let's color code this too. I'm going to do f in blue, g in red, and t in purple. So I might say f of x is something squared, x squared, minus 3, right? Then inside of, I have to put something inside of f, right? 2 things basically nested. And you can kind of see that inside here has sort of the structure of something plus 1. So you could let that just be the next function. You could let g of x be something, x plus 1, right? And then the last function, the something, basically just needs to be the cube root of x. So literally if you take this, right, and you pop it in here, and then you get your result, and then you pop it in here, you would have the h, right? And you could even have done that different ways. You could have said g is the cube root of x, and then t is literally just x. That's fine, right? T of x equals x is a function. And I could put that in here, and I get exactly that, right? Then I could take this and put it in here, and I would have it again. And there's other ways to do it too, but that's probably one of those 2 is the most clear way I would say to do it. Then for this one, I feel like a lot of times it's easier to probably build things up. Basically here, I'm just going to do f of g of h, but h is x over 2, right? So then if I do g of x over 2, that's just 4 minus 7 times x minus x over 2, right? Because that's all you do with the input here. You just put the input in right next to the 7, like I did. Then you're just going to do f of that, right? And so f is literally just like a times 10 function. So whatever your input is, you just multiply it by 10. So you do 10 times 4 minus 7 times x over 2, which you could simplify if you want. 40 minus 70 over 2x, something like that if you want. But yeah, that's fine too. So nothing wrong with doing 3 compositions or 4 compositions. Totally okay. Another thing that you're going to run into a lot is evaluating compositions. So, in those previous problems up to this point, everything was just, of x and stuff. Here too, of x. So here, though, it's g of h of 24, right? And so with stuff like this, you'll save yourself a lot of time if you just do it one thing at a time. So what I would do first is I would do h of 24, right? Which, if you do 24 squared plus 1, you'll get 577. Then now you literally just go take this thing, right, and you multiply it by 3, and you'll see that you get 1,731. So it's a lot easier than honestly doing putting h inside of g and then plugging in the number. I would plug in the number to the innermost thing, then get your result and just keep going and plug it into g. So here for 3 functions, what I mean by that is, that's kind of how I would think about it. I would do h of 2 first. H of 2 is literally just 2 squared plus 1, so 5. And then, so many parentheses, so I get a 5 from that. And then g of 5 is just 3 times 5, right? So 15. And then you get 15. And then f of 15, right, is just going to be like the 2 times 15 minus 1, or just 30 minus 1, which is 29. So I'll just do it like this. So that's just kind of how I go about, and that's how I would want you to go about evaluating compositions. Don't go and just get this as a function of x and then plug in. I mean, you should get the same answer, right? Like if you just fully figured out what f of g of h of x is, it would just be some big messy thing like 2 times 3 times x squared plus 1, and then, let's see, minus 1 there. So you would have to multiply all that out a little bit, right? And it's more work than you need to do. Whereas instead you could probably be doing this just in your head, right? So this is not the way I want you to do it. I want you to just do it exactly like I did here. All right. So this is the last one I just kind of want to go over. And here I give you 2 functions f and g. And I just want you to be able to evaluate also from pictures. So all of these are units of 1 in the grid here. And so this one says find f composes g of 2. So what you'd have to do here is start off and find g of 2, right? So go to g, go to 2, and get your number, -3, right? Then you now are finding then f of -3. So go to -1, 2, 3, and look at f, and you get 1, and that's that one. And then for this one, you want g of f of 1. So now we're starting here, right? And we're doing f of 1 first, which is 0. And then we're going to do g of 0, right, which is up here at 2. And so then, well, wait, there was already an equal sign on that one for some reason. And that's it. So again, just kind of on this one, it was f of 1, which is 0, right, has 0 output. And then I go over to 0 input now, and I get 2. If I wanted to do this one symbolically, basically what I just did was this. I went through f first, then I went to g, and what happened is 1 went to 0, and then 0 went to 2, right? That's basically how that works. So I think that should be enough examples to kind of get a sense of how this composition thing works. We will use this next time to help us kind of understand what an inverse function is. And then from there, we'll be able to actually get into really the meat of the unit, which is studying root functions, which act as inverses, which I would put in quotes if you could see me, to polynomial functions that we just studied for a long time.